In the 1860s, chemists worked in a world of scattered data. They had identified about 60 distinct elements, each with unique properties, but they lacked a standardized system to categorize them. Early attempts at organization often focused on atomic weight or small clusters of 3 elements. While these systems worked for a few specific examples, they eventually collapsed when applied to the full list, leaving behind outliers that didn't fit the proposed patterns. Researchers assigned every element a shorthand symbol, but at the time, an element's name, weight, and chemical behavior were treated as independent facts. There was no known link between the identity of an element and its place in the broader physical world. It was the scientific equivalent of having 60 pieces of a jigsaw puzzle without the image on the box to guide the assembly. Without a unifying rule to explain these connections, the study of elements remained a reactive science, a meticulous inventory of what had been found, rather than a system that could point toward what was still missing. Dmitry Mendeleev, a Russian professor, tried a different approach while writing a textbook for his students. He treated the elements like a deck of cards, writing the weight and properties of each one on a separate slip of paper, so he could physically rearrange them on his desk. As he sorted the cards by increasing weight, a pattern emerged. Specific chemical behaviors began to repeat at regular intervals. Mendeleev began a new row every time a behavior repeated. This created a grid where horizontal rows, or periods, tracked increasing weight, and vertical groups clustered elements with similar chemical traits. We can see this iterative process in Mendeleev's original manuscript. His handwritten notes show the early rows and columns taking shape, with symbols and question marks as he worked to align the repeating behaviors. This sorting method revealed that the properties of elements aren't random. They follow a cyclical rhythm built into nature. Mendeleev's most significant move wasn't how he arranged the elements we knew, but how he handled the ones we didn't. When the pattern dictated that an element should exist where none had been discovered, he refused to move the next available element into that spot. Instead, he left empty squares in his grid, insisting these gaps were undiscovered elements. He used surrounding elements to predict their exact weight, density, and reactivity. The proof arrived years later when gallium, scandium, and germanium were discovered, matching his predictions perfectly. By successfully mapping out the unknown, the tables shifted from a classroom visual aid into a validated framework for understanding the recurring patterns of the physical world. Mendeleev's table wasn't quite finished. Because he relied on atomic weight, there were a few spots where he had to manually swap elements to keep them in the correct behavioral columns, even though the weights didn't perfectly align. 50 years later, physicist Henry Moseley identified the missing link. He discovered the true organizing principle isn't weight, but atomic number, the count of protons. This resolves Mendeleev's inconsistencies, aligning elements into distinct families we recognize today, from highly reactive alkali metals on the left to stable noble gases on the right. This adjustment showed that Mendeleev's intuition was correct. He had identified the right pattern, even if he didn't yet have the subatomic tools to explain why it worked. This leaves us with a deeper question. Why does this repetition of behavior happen at all? The repeating behavior observed on the table is the direct result of how an atom organizes its internal layers of electrons. An atom's outermost electron layer, the valence shell, dictates its chemical personality. It controls trends like atomic radius, or size, and electronegativity, how strongly it attracts other particles. This shell determines how an element bonds and if it becomes a charged ion. The periodic table is essentially a large-scale map of the atomic world. In the next lesson, we'll look past the grid and dive into the microscopic structures that make these patterns possible.